So we know we can like add vectors together. That's pretty straightforward, right? If I have something like this, how do you do that one?
You just add
Add what exactly? Yeah. Add the, how would you describe it? Maybe the x and y components respectively, right? So like 3, 5. And this is something we got to be careful of. Like when we introduce a new sort of system, we do approach them differently. Like when you add numbers together, that's different like when you add fractions together, right? What's a common mistake when you add fractions together where you kind of add both the numerator and the denominator or something like that, right? Whereas with vectors, we actually do kind of add their respective components together, right? So you just got to kind of be aware of how everything works when you introduce a new system. And so adding and subtracting work very similarly. Multiplying is a little bit trickier because multiplying, right? You would have learned multiplication like this. Is that right? Something like that? And how would you do that one?
You just times the top number.
Yep. So 5, 10, right? But then, what if we went back to this example? What if we wanted to multiply 2 vectors together? Because the issue is here, right? When you look at this one, that's not multiplying 2 vectors together. What is this type of quantity when it's just a number? We call that a scalar. So a scalar is just a number, right? But what happens when you want to multiply 2 vectors together? What are we going to do? There's a few ways that we can approach it. One of them is algebraically, one of them is visually, and the third one is kind of intuitively. And that's what I'm talking about, how everyone has different ways of understanding them, right? If we just want to look at algebraically, it's one of those ones which is actually, the process itself is quite easy to follow, right? But actually understanding a grasp of what the dot product, or we call it the scalar product as well, is doing is quite tricky. So that's why I'll talk a bit about that in the next couple of lessons, right? But just to mention, this one here, we tend to call a multiplication by scalar, right? Because you're multiplying by a scalar. But we call this one a scalar or dot product. That's why we try to use different terms, because if you call it a scalar product, people might get confused with this one. So we call this one the dot product usually, when you're multiplying 2 vectors together, and we put a dot there in between, right? Algebraically, and the reason why we call it dot product is there's actually other types of multiplication as well. It's something called the cross product that we don't do in this course though. But algebraically, what's going on? Let's say we had 2 vectors. Let's say we had A and B. And what basically happens is we're going to apply a similar method here. We're going to only look at the x and y components, and what I'm going to do is the dot product between them is the 2 x components multiplied together, and I'm adding the 2 y components multiplied together, right? That is my formula for what we call the scalar product. And so we could look at an example for this one. That would just be 1 times 2 plus 2 times 3. Right? And that's going to give me 8. Notice though, what type of answer are you getting out of this? A whole number, right? So we start off with 2 vectors, we're taking their dot product, and we're getting a whole number, which is kind of interesting because with these ones, we've kind of gotten vectors as our answers. So that's something to think about as well. Does this number have much meaning? It does. That's when we'll look at the visual one in a moment. But let's just have a look at a few examples how you might do these. Interestingly, the cross product does end up giving you a vector. So that's just something to think about there, right? So let's look at these ones. Just something to be aware of. When we looked at vectors last time, there's actually a whole heap of different notations you can look like. So this one here we call the column notation. For good reason, because essentially you've got your x and y components and they're written in a column, right? This one over here, I don't know if you guys remember this one. Do you guys remember what the i's and j's sort of represent? Does that look familiar to you guys? What do they mean? Do you remember?
The i's are like the top number and the j's like the
Yeah.
Yeah, like the x and y.
They are the x, y, and this is where you're going to be careful because in extension 2 we looked at I components, and that was the imaginary axis, which was the vertical axis, right? But in our vector format, actually, the i's and j's correspond to the horizontal and vertical components. So that's just sort of be aware of that distinction. So we call this component form. Right, and so essentially this is like the horizontal one, and this is the vertical one. And we essentially call them like unit vectors, because the idea of what's going on is like if you drew up your axis, essentially what's happening is you've got this vector here, this is your I unit vector we call it, and this is what we call the J unit vector, and they're saying they basically go to the point 1, and then what happens when you multiply, for example, a vector by a number, so like 3 times I, well, it's going to be 3 times as long, so it goes across to the point 3. That's basically what it's saying. Yeah, it's just a fancy way of writing that out. It's a different way. This one here, we can also write them not only in the column notation, but kind of similar to your standard coordinates. So that's again, you've got to be careful. Are you looking at a vector? Are you looking at a point? You got to sort of look at the context of what you're looking at, right? Let's do this one here first, but same idea, right? We can say that A dot B would just be, okay, so the 2 x components multiplied together, so like 2 times 3 plus 4 times 1. And this one looks like it's going to be 10. Some good maths there. Caitlin, want to try the next one for you? That's right, and just be careful though, because when you're writing it out, I'm not sure how you wrote it out though, basically we're only interested in the sort of coefficients, right? So kind of similar to this one, you should just get a number. So even when you're writing this out, you could just write it 3 times 1 plus 2 times negative 4. Right? So you're not multiplying the actual components themselves. Yeah. Yeah, negative 5, that's it. So now that's our first negative result, right? And we're going to look at what that actually indicates when you're looking at 2 vectors. Because don't forget, at the end of the day, you're not just doing a process, you're not just doing a calculation, you are actually looking at 2 vectors. And 2 vectors should have some sort of representation on a visual sense. And a negative dot product, we'll have a look at what that actually means in a second. All right. Next one over here. This one's a bit different. What's going on here? How did you change them, Ken?
I changed it into the exact value.
Yeah, right. So hopefully these angles should be familiar, like 30 degrees and 45 degrees, right? So like Lily, if you put in your calculator, cos 30, for example. I'm not sure if you're in degrees or radians, but yeah, degrees, that's fine. And put in cos 30. Yeah, so you get like a decimal like that, but hopefully that decimal is familiar. That's right, it is root 3. So if you put in root 3 and 2 in your calculator, Caitlin, nice. If you put in root 3 and 2 calculator, it actually is the same thing. So cos 45 and sin 45, those are also the same. Caitlin, do you remember those ones? What? Cos 45 and sin? Yep. Yeah, that's right. Or 1 and root 2, either way. So what I might do is, because remember I said that we can write vectors any way we like, right? What I might do is I might still just write that as a number, so that's a bit more clear what's going on there, because I think the cos can kind of confuse you a little bit. So just remember that that's the same as root 3 on 2. So you might want to change that first. And then that's sine 30 is going to be, what's sine 30 again? Half? Yeah, yes. And V is going to be 1 over root 2 and 1 over root 2. Alright, so far so good. So then we can probably simplify these a bit. So U is going to be 3 root 3, and this will just be minus 3. And V is going to be negative 2 on root 2 and negative 2 on root 2 as well. Alright, perfect. So now this is the fun part. Now I get to put them together. even though that they're like kind of surds and there's fractions here going on here, we can still combine them, right? There's no reason why we can't. We just need to remember, okay, what does it mean when we've got the dot product? We've got these two x components put together and these two y components put together as well, okay? Gonna be 3 root 3 times negative 2 on root 2 plus negative 3 times negative 2 on root 2. And it should be consistent, it should be x's. So that's going to give me 6 root 3 root 2 plus negative 6, no, positive 6, sorry, on root 2. Is that looking alright? And then, did you put them together first, or did you? Yeah, okay. So that's negative 6 root 3 plus 6 on root 2. And then we can rationalize that. So multiply top and bottom by root 2. It's looking pretty interesting. Is this looking similar to what you got? And then did you simplify something? Or?
I had negative 6. No.
What's up? Did I do something wrong?
No, it works.
Yep.
This would be negative 6 root 6 plus 6.
Okay, cool.
Square root 2.
Yep.
And then if you divide that by 2, then it equals negative 3 root 6.
Yeah, expand it out, and then so negative 3 root 6 plus 3 root 2. Okay, cool. Perfect. Alright, awesome. So that's just like a trickier example with our scalar product in the sense that the principle is the same, but you might just be doing a bit more complex sort of calculations, I suppose, with the numbers themselves, right?